Electricity is vital to our civilization. So what is electricity and how does it work? To explain electricity, we need to zoom past the molecular and into the atomic level. Atoms are the smallest things we can kind of see. To really understand electricity, we must go even further and look inside an atom. This is where it gets complicated, because the inside of an atom cannot be seen, at least not at the time of writing. So we will use this representation of the inside of an atom. This is called the Bohr Model. Keep in mind that it is not to scale and only two-dimensional. This model is also known as the planetary model, modeling the parts of an atom as planets orbiting a sun or moons around a planet. Atoms consist of protons and neutrons. These form the nucleus of the atom. Orbiting the nucleus are the electrons. It's these electrons that are responsible for electricity, hence the name. What type of atom, which element it is defined by the number of protons in the nucleus at the center. Atoms of one element all have the same number of protons, but can have different numbers of neutrons and electrons. It's this variable number of electrons that is important to our understanding. Electrons, which are far lighter than the protons in the nucleus, can relatively easily move. And this is important because the movement of electrons is what forms an electric current. The atom's protons account for the positive charge of the nucleus, and the electrons for the negative charge. In a stable, resting, or rather neutral electrical condition, these charges balance each other out within the atom. This gives the atom a net electric charge of 0. For each positive proton, you will find one negative electron. In this state, the atom is at its lowest possible energy level. However, we can change the atom's charge or energy level by causing it to gain or lose electrons. When the atom has fewer electrons than protons, it becomes positively charged. But when the atom has more electrons than protons, the net charge swings back the other way and it becomes negatively charged. More electrons than protons mean the atom is negatively charged. Fewer electrons than protons mean it is positively charged. Losing or gaining electrons changes the atom's electric charge.
We like to divide materials into two categories: conductors and insulators. A conductor is a material that freely allows the flow of charge. An insulator is a material that does not allow the flow of charge. Either type of material can become charged. What matters is whether or not the charge can move once it's there.
Materials with high electron mobility are called conductors. Materials with low electron mobility are called insulators.
Like most things, materials fall on a spectrum. Conductors on one end and insulators on the other. No material is a perfect example of either type, but the three best conductors are silver, copper, and gold, in that order. It's no coincidence that those all fall in the same chemical group. They each have one very loose electron on their outer edges. That alone doesn't make them a good conductor, though. A material isn't made of one atom, it's made of a bunch of them. We need to see how those atoms work together. Atoms are always bonded by their electrons. In metals like copper, the electrons tend to form one big cloud for the entire material. Specifically, the energy levels. In a single atom, electrons can be in a variety of energy levels. But when atoms are together in materials, those levels are separated into bands: a conduction band and a valence band. What separates conductors from insulators is how much energy it takes for an electron to jump from the valence band to the conduction band. For insulators like glass, the gap is really big. In semiconductors like silicon, the gap is small. In conductors like copper, there is no gap. Valence electrons are conduction electrons. That's what makes them so conductive. There are already electrons in the conduction band ready to go. If they get a reason to move through the material, they'll do it.
A commonplace object where you can see an insulator and conductor working together is in a simple wire. This electrical wire has a copper core and a plastic shell. Copper atoms have a very loosely bound electron on the outside, as seen here again using the Bohr model. This makes copper a perfect conductor, whereas the plastic is an insulator. The millions, if not billions, of copper atoms in this piece of wire easily exchange electrons, allowing us to make an electrical circuit with it. Think of an electrical circuit as a path that connects 2 points with a possible charge imbalance, usually connecting a negatively charged point to a positively charged point. Like marbles in a tube, moving from a high place full of marbles to a low place lacking marbles. Imagine these marbles all along the circuit, each marble being an electron. These marbles originate from a power source, for instance a battery. And we'll explain how batteries work exactly in a future video. Electrons move from the negative to the positive, as we've established earlier. The battery pushes out electrons from one end and attracts them from the other. As one is pulled in, one is pushed out. Despite the electrons moving relatively slowly, this effect causes the energy to be transferred almost instantaneously. To create such a flow of electrons, we must provide them a path with a conductor, such as the copper within our wire. If this path is blocked by an insulator, such as plastic, rubber, or air in the case of a cut wire, the electrons cannot continue to flow, stopping the electric current. The key to the flow of electricity is making a continuous electrical circuit, connecting a wire between a source of electrons and an attractor of electrons. All electrical devices are powered this way. That is why your battery has 2 poles, a source and an attractor, a negative and a positive. This is also why your electrical plug has at least 2 tongues, one for incoming electrons, one for outgoing. You see, electrons are not spent, they do not cease existing. They are mere carriers of charge and can only be useful on their way to their destination. Take note that connecting 2 poles of a power source directly can actually be very dangerous. This is what's called a short circuit, because there is nothing between the source and the destination of electrons to power, such as a lamp or television. This means that the electron flow will not encounter any resistance. The release of energy when short-circuiting is therefore instant, often paired with the involved wire heating dangerously. This is why buildings and some devices have fuses. These automatically cut the current flow when the current becomes too high, preventing damage or worse.
Let's consider water. Say you've got a long pipe with some water at rest inside. The water molecules look like this, moving around randomly. If the water begins to move through the pipe, the molecules move too, because they're what make up the water. They still have the random motion, but they now also have forward motion. A similar thing happens with the charge in a copper wire. That wire is full of conducting electrons, just like the pipe was full of water. Individual electrons are conducting around the copper randomly. If we connect a power source though, it'll act like a pump. The electrons will still have the random motion, but also some forward motion. Then water flow is a good analogy for electric current. So good, in fact, it has a name, the hydraulic analogy. There's a hydraulic equivalent for every circuit component you could imagine. It's kind of fascinating. Just like objects can have mass or temperature or speed, objects can also have charge. It's just a property. Things like balloons, hair, or pieces of plastic become charged by transferring electrons. We rub a balloon against someone's hair, the balloon and the hair become attracted to each other. Now that they're charged, they don't even need to touch to affect each other. Unlike mass though, charge has 2 different types or flavors. We call these 2 types positive and negative, but only for mathematical convenience. They're just labels. We could have just as easily called them up and down, or good and evil, or dingleberry and snozberry. The snozberries taste like snozberries. The 2 types show opposite behaviors, so as long as the labels are opposites, we're fine. It doesn't even matter which ones we label which. The labels we use today were decided 270 years ago in 1748 by Ben Franklin. It might have been better to label them the other way, but now we're stuck with it. Thanks, Ben Franklin. Opposite behaviors. Opposite charges attract, and like charges repel, which I think is pretty common knowledge at this point. That's what makes atoms the way they are. The protons are positive, and the electrons are negative, so they're attracted to each other. Unfortunately, since electrons are the things that move around and electrons are negative, we kind of have to think backwards. An electron gain makes an object negative, and an electron loss makes an object positive. The balloon from earlier gained electrons from the hair, so it became negative and the hair became positive.